First, electricity. The section on electricity is divided into energy transfer in circuits, mains electricity, and electric charge. First, energy transfer in circuits. Here's a quick reminder of what circuit diagrams and their component parts look like. To start with, these are some of the standard symbols used in the electrical circuits you might see in your exam. You'll also need to use them yourself if you're asked to draw a circuit diagram. They are a single cell battery, a switch, two symbols for a lamp, a fixed resistor and a variable resistor, and an ammeter and voltmeter. Here's a simple circuit with a battery, a switch and a lamp connected in series. When the switch is closed, a current begins to flow, pushed around the circuit by the battery. The current leaving the battery is the same as the current returning to the battery. Because all the components in the circuit are connected one after the other in series, the current is the same everywhere in the circuit. In this case, 0.2 amps. Current is measured in amps, with an ammeter, which can be connected in series with each component to measure the current flowing at that point. This is a parallel circuit, where the current can split up and go around different branches of the circuit. The current flowing in different branches can be different depending on how easy it is for the current to flow that way. Ammeters connected in different branches of the circuit will show different measurements. One thing we do know is that the total current flowing into any point in a parallel circuit is the same as the total current flowing out of it. For example, at the junction where the wires join, there's 0.6 amps flowing into that point and 0.2 amps flowing out down one branch and 0.4 amps flowing out down the other. That's 0.6 amps altogether flowing out from that point. Next, we'll look at ways of changing the current in a circuit. The current in a circuit can be changed either by changing the voltage or by changing the resistance in the circuit. First, changing the voltage. We're most familiar with the voltage in the case of a battery, where the voltage is the difference in energy between its two terminals. In fact, voltage is the difference in the energy between any 2 points in a circuit. Voltage is measured in volts with a voltmeter. To measure the voltage, you connect the voltmeter in parallel with the component. In this case, the voltage across the battery is 6 volts, while the voltage across each lamp is 3 volts. More battery cells in the same circuit mean a higher voltage and a bigger current. In this circuit, if the battery produces 3 volts, the current is 0.1 amps. If it's 6 volts, it's 0.2 amps. And if it's 9 volts, it's 0.3 amps. The other way of changing the current in a circuit is to change the resistance. One way to do this is to change the number of components, such as bulbs, in the circuit. Bulbs are designed to offer resistance to the flow of electricity. That's why they glow. More bulbs in the circuit means a greater resistance and smaller current. Adding different resistors in the circuit can also change the resistance in the circuit. The greater the resistance, the smaller the current. Resistance is measured in ohms, written using the Greek letter omega. An easier way to change the resistance is to use a variable resistor that can change its value. Again, the greater the resistance, the smaller the current. The smaller the resistance, the greater the current. Resistors are specially designed to offer resistance to the flow of current. They're used in electric and electronic circuits to control the flow of electricity through the different components. In a circuit, energy is spent overcoming resistance. This energy is given off as light or heat, which is made use of in light bulb filaments and in the heating elements of kettles, hair dryers and other heaters. As well as the components, like bulbs and resistors, the connecting wires themselves have some resistance. Thin wires offer more resistance to current than thick wires because they have less space for the current to flow. Long wires have more resistance than short wires of the same thickness. So, to summarise energy transfer in circuits. Current is measured in amps, and it's not used up as it passes through components. The current in a series circuit is the same everywhere. The current in a parallel circuit splits up to take different routes. More current takes the easier route, that offers less resistance. In parallel circuits, the total current into any junction equals the total current out of the same junction. More cells in a circuit mean a higher voltage and so a larger current. More components in the circuit mean a greater resistance and so a smaller current. Short wires have less resistance and carry more current than long wires. Thick wires have less resistance and carry more current than thin wires. There's a special relationship between the voltage, current and resistance in a circuit called Ohm's Law. Ohm's Law says that anywhere in a circuit, V equals I times R, where V is the voltage across a component in volts, I is the current going through the component in amps, and R is the resistance of the component in ohms. If you know any two of these values, you can work out the other one. A good way to remember Ohm's law is to put the values in a triangle like this, with V at the top in the vertex and R on the right. So V equals I times R. I equals V divided by R, and R equals V divided by I. Another way of stating Ohm's law is to say that the voltage is proportional to the current, as long as the resistance and the temperature stay the same. If we plot a graph of current against voltage for a normal resistor, it's a straight line. As you increase the voltage, so the current increases in proportion. Double the voltage and it doubles the current. A bigger resistance needs a bigger voltage to push the same current through it. The graph will still be a straight line, but with a flatter gradient. You might have spotted that the straight line graph continues into the negative quadrant. What do you think that means? When the straight line graph is in the negative quadrant, the voltage across the resistor is negative, which means it's been connected the other way round. The graph also shows that the flow of current is negative as well, which means that when the resistor is connected the other way round, the current just flows the opposite way through it. There's more about Ohm's law in the physics part of the higher tier science programme. That's the end of energy transfer in circuits.